Could a caveman learn to read and write? It's a simple question. It sounds like a joke. You picture a guy in a bearskin, club in hand, scratching his head at a copy of See Spot Run. It seems impossible. But the answer is more complicated and much more interesting than a simple yes or no. The answer tells us a story about ourselves. It tells us about the brain we all share and how it learned the most amazing trick it knows. First, we have to be clear about who we mean by caveman. This isn't just one type of person. The term covers a huge span of time and several different human species. Are we talking about Homo habilis from 2 million years ago? Or a Neanderthal from 40,000 years ago? Or an early Homo sapiens, a person like you and me living in a cave in Europe around the same time? Let's start with the easiest case. Let's talk about an anatomically modern human, a Homo sapiens from about 50,000 years ago. These are our direct ancestors. If you gave one a shave, a haircut, and a modern set of clothes, he or she could walk down the street and you wouldn't look twice. They were us. The most important thing to understand is this: their brains were the same as our brains. Not similar, the same. The physical hardware inside their skull was identical to the hardware inside yours. Same size, same shape, same basic wiring. All the key parts were there. They had a frontal lobe for planning and decision making. They had a temporal lobe for processing sounds and language. They had an occipital lobe for seeing. Think about language. We know they had it. Their brains had Broca's area and Wernicke's area fully developed. These are the two key language centers in the modern human brain. Broca's area handles the production of speech, the physical act of forming words. Wernicke's area handles comprehension, understanding what words mean. Damage one of these, and a person's ability to speak or understand is severely damaged. Our caveman ancestor had both, ready to go. They also had the right genes. A gene called FOXP2 is critical for fine motor control of the mouth and larynx, which you need for complex speech. Our version of this gene is different from that of chimpanzees, and the version found in the DNA of these ancient humans. It's the same one you have. The evidence from fossils, genetics, and archaeology all points in one direction: these people talk. They likely had complex languages with grammar and syntax. They told stories. They gave each other names, they gossiped, they lied, they were fully human. So, let's do a thought experiment. Imagine we could travel back in time and bring a newborn baby from one of these groups into our world. We raise this baby in a modern family. This child would grow up just like any other child. It would learn to speak English, or Japanese, or whatever language was spoken in the home. It would hit all the same developmental milestones. It would learn to use a spoon, play with toys, and get into trouble. And when this child went to school, what would happen? They would learn the alphabet. They would learn to connect the shape of the letter A to the sound it makes. They would learn to string those letters and sounds together to form words. They would learn to read. There's absolutely no biological reason to think they couldn't. The capacity for reading and writing is not a special new addition to the human brain. It's a trick we taught our old brain to do. This is the core of the whole issue. Reading is not an instinct. It is an invention. Humans have been speaking for a very, very long time. Maybe hundreds of thousands of years. But we've only been writing for about 5,000 years. That's a blink of an eye in evolutionary time. Evolution doesn't work that fast. You can't evolve a whole new brain module for a specific skill in just a couple hundred generations. There is no reading center in the brain that was put there by evolution for the purpose of reading books. It can't exist. So how do we do it? How can a brain that evolved to hunt mammoths and avoid lions learn to read a text message? The answer is a concept called neuronal recycling, or you could call it neural reuse. And it's a fancy term for a simple idea: the brain is good at repurposing its existing parts for new jobs. Think of your brain as a workshop full of tools. These tools evolved over millions of years for very specific tasks. You have a tool for recognizing faces. You have a tool for understanding spoken language. You have a tool for controlling your hands with great precision. You have a tool for navigating your environment. When writing was invented, the brain didn't grow a new tool. It just picked up several of its old tools and used them in a new combination. Reading is a clever hack. It hijacks brain circuits that evolved for other things. Let's break down what happens when you read. First, your eyes see a bunch of squiggles on a page. Your visual cortex processes these shapes, but a specific part of your visual system, an area on the left side of your brain, gets really good at this. Scientists call it the visual word form area, or the brain's letterbox. This little patch of neurons learns to recognize letters and combinations of letters with incredible speed. What was that brain area doing before we learned to read? It was recognizing objects. It was part of the system that helped our ancestors identify a spear, a fruit, or the footprint of a predator. When we learn to read, we are essentially training this object recognition system to specialize in a new kind of object letters. We are recycling it. The letters C, O, and U are just shapes, like a circle or a snake or a cup. Our brain learns to see them as special objects, but recognizing shapes isn't enough. The next step is to connect those shapes to sounds. Your brain has to learn that the squiggle S makes a hissing sound. This job involves another set of recycled pathways, connecting the visual system to the auditory processing centers, the same ones you use to listen to speech. Yes, where phonics comes in, you are building a bridge between two completely different parts of the brain that didn't originally evolve to talk to each other in this way. Once you have the sounds, you have to connect them to meaning. The string of sounds, ka, has to trigger the concept of a small furry animal in your mind. This part of the process hijacks the language system that was already there. Your brain's existing dictionary of spoken words gets a new front door. Before, the only way to access the meaning of ked was to hear someone say the word. Now you can access it by seeing the word written down. This whole chain of events is an invention. It's a piece of cultural technology, like the wheel or the computer. And just like a computer, it requires a user to learn how to operate it. Learning to read is the process of building and strengthening these new connections in your brain. It's hard work. It takes years of practice for a child to become a fluent reader. That's because the brain isn't naturally built for it. We have to force it. We have to carve these new pathways through practice and repetition. This is also why some people have disorders like dyslexia. It's not a sign of low intelligence. It's often a problem with one of the links in this chain. Maybe the connection between the visual shape of a letter and its sound is a bit fuzzy. The brain is struggling to make that specific, unnatural connection work smoothly. If reading were a biological instinct, like seeing or walking, dyslexia wouldn't exist in the same way. Nobody has dyslexia. So, back to our time-traveling caveman baby. Raised in our world, their brain would be just as capable of this neuronal recycling as yours or mine. They would have the same object recognition circuits to turn into a letterbox. They would have the same auditory centers to link sounds to. They would have the same language centers to provide meaning. They would attend preschool and learn their ABCs. They would struggle with some words and breeze through others. They would, with time and effort, learn to read and write. They could become a poet, a novelist, or a software engineer. The biological potential is 100% there. Now, let's ask a harder question. What if we don't bring the baby to our time? What if we travel back to 50,000 years ago, find an adult caveman, and try to teach him to read? This is a different story. Not because his brain is different, but because his world is. His brain is the same hardware, but it's running completely different software. His mind has been shaped by a lifetime of different experiences and needs. This adult's brain is highly optimized for his environment. His visual cortex isn't trained to see the subtle differences between P and Q. It's trained to spot a deer hiding in a thicket from 100 yards away. It's trained to read the clouds to predict the weather. It's trained to see tiny variations in the mud that tell him which way an animal went, how big it was, and how long ago it passed. His intelligence is immense, but it is a physical, environmental intelligence. His memory isn't filled with facts from books. It's an encyclopedia of his landscape. He knows every rock, every stream. He knows which plants are medicine and which are poison. He knows the life cycles of dozens of animals. This knowledge is stored in stories, songs, and traditions passed down orally from generation to generation. His culture is based on listening and remembering, not reading and referencing. So, if you showed up with a book, the first barrier would be conceptual. Why would he need this? What is the point of making marks on a surface to represent sounds? It's a solution to a problem he doesn't have. His world doesn't have a complex economy that requires contracts and ledgers. Like, it doesn't have a centralized government that needs to post written laws. Knowledge is shared face to face. But let's say you could convince him. Let's say he was curious and willing to try. Could he learn? Yes, probably. But it would be incredibly difficult. An adult brain is less plastic than a child's brain. It's harder for adults to learn new languages, and learning to read is like learning a new language for the eyes. You'd have to slowly and painfully build those new neural pathways that a child builds more easily. His object recognition area would have to be retrained. It would be a frustrating and slow process. He might give up. He might never become a fluent reader, but the potential is there. His brain is capable of it. The main obstacles would be motivation and the reduced plasticity of an adult brain. Now let's get even trickier. Let's talk about a Neanderthal. Neanderthals were not our direct ancestors. Yes, they were a sister species, another kind of human who lived in Europe and Asia for hundreds of thousands of years. They disappeared around 40,000 years ago, about the time modern humans were spreading across the continent. Could a Neanderthal learn to read and write? This question is much harder, and we can't be as certain. Their brains were not identical to ours. On average, their skulls were actually slightly larger than ours. But they were shaped differently. They were longer and lower, whereas ours are more rounded and tall. This different shape implies a different organization. Their occipital lobes, the part for vision, seem to have been larger than ours. Their parietal lobes, which handle sensory integration, may have been smaller. What does this mean? We don't know for sure. Some scientists think their larger visual system was an adaptation to the lower light levels of Ice Age Europe. Maybe they were, in a way, more visual thinkers than we are, but we do know they had a lot of the same key ingredients for complex thought. We have found their DNA, and it turns out they had the exact same version of the FOXP2 gene that we do. This strongly suggests they had the capacity for complex speech. The hyoid bone, a small bone in the throat that supports the tongue and is crucial for speech, was the same in Neanderthals as it is in us. Their behavior also points to symbolic thought. They made sophisticated tools. They controlled fire. They hunted large, dangerous animals in coordinated groups. They buried their dead, sometimes with objects like flowers or animal horns. This suggests they had rituals, and maybe some concept of an afterlife. They made jewelry from eagle talons and shells. They painted on cave walls. All of these things, language, ritual, art, are forms of symbolic communication. You are using one thing to represent another. A grave represents the memory of a person. A painting of a bison represents the real animal. This is the exact same cognitive leap required for writing. The letter A is just a symbol that represents a sound. A word is a symbol that represents a concept. A Neanderthal clearly had this capacity for symbolic thought. So if we raise a Neanderthal baby in our world, could it learn to read? I would lean towards yes. They had the foundational ability, symbolic thought, and probably complex language. The process of neuronal recycling would still work. Their brain would hijack its object recognition areas to create a letterbox, just like ours does. But it might be different. Maybe their learning process would be slightly different. Perhaps their larger visual cortex would make them exceptionally good at recognizing the shapes of whole words, but maybe their differently organized brain would make it harder to connect those shapes to sounds. We are deep in speculation here. We can never know for sure. But there's no compelling reason to think it would be impossible. The basic building blocks seem to have been in place. A Neanderthal was a human, just a different kind of human. The odds are good that their brain was flexible enough to learn this new cultural trick. The story of learning to read is not a story about biological evolution. It is a story about cultural evolution. Our brains, both ours and those of our ancient relatives, were a platform. They were a powerful, general-purpose computer. For most of human history, that computer ran a very specific set of programs for survival. How to find food, how to make tools, how to navigate the social world of a small tribe. How to remember 1,000 square miles of territory. These are not simple programs. They require incredible intelligence and memory. The skills of a hunter-gatherer are vastly complex. An ancient human's mind was not empty or simple. It was full of a different kind of knowledge. Then about 5,000 years ago, someone invented a new program. This program was called writing. It started as a simple accounting tool for farmers and merchants in Mesopotamia. Little pictures to represent a sack of grain or a head of cattle, but this program was a virus. It was too useful to stay contained. It spread. It evolved. The pictures turned into abstract symbols. The symbols were linked to sounds. It became a way to record everything: laws, history, poems, and stories. This new software fundamentally changed human society. It allowed knowledge to be stored perfectly, outside of the fragile human memory. It allowed a person's thoughts to travel across vast distances and across thousands of years. The world we live in today, a world of science, global communication, and complex societies, is built on top of that program. It's impossible without writing. When we teach a child to read, we are installing this ancient program onto their biological hardware. We are rewiring their brain, connecting up the old parts in new ways to run this powerful piece of cultural software. And the amazing thing, the thing that answers our question, is that the hardware hasn't really changed. The brain of a child learning to read in a classroom today is the same brain that was learning to track a deer in a forest 50,000 years ago. So, could a caveman learn to read and write? If by caveman you mean an early Homo sapiens, one of our direct ancestors, the answer is a definite yes. A baby brought to our time would learn it just as we do. An adult in their own time would find it hard, but their brain would be capable of it. If by caveman you mean a Neanderthal, the answer is a confident probably. The evidence suggests they had the mental tools required. The question isn't about whether they were smart enough. They were clearly brilliant, their intelligence was just applied to a different set of problems. The question is about the stunning adaptability of the human brain. It's a machine built for survival that we have taught to do magic. It takes the grunts and gestures of our ancient past and turns them into poetry. It takes the part of the brain that recognizes a footprint and teaches it to recognize a word. It's the greatest trick the human mind ever learned, and the evidence is strong that any human from any time in the last 100,000 years had a brain that was ready for the lesson.